we're going to be learning about one of the last set of methods in unsupervised learning. And so this class of methods is going to be called k-means, and at the end of today's lecture, we'll learn about a new class of machine learning models called latent variable models. And the learning algorithm for these is the EM algorithm. So just some announcements. Today at around 5 p.m. or so, we'll release one more survey for the ethics module. So that's like a quick 2-minute survey. And if you've done it for another class, you don't need to do it again for this one. You get credit for it. And on Friday, your reflections are due. Any questions about assignments, homework, administrative aspects of the class? Everyone know that we have a final exam on the 14th, 9 to 12? Okay? Yeah? I think it's the 14th. Yep, it's a Thursday, so yeah. So don't miss it, but it's okay if you show up a day early. Okay, so we'll kick us off with k-means for clustering. And so today we'll cover k-means, GMMs, EM. We're not going to get into why EM works, but I'll leave the slides in there for you to review. And that's going to be particularly helpful if any of you are going on to taking 412. Out of a show of hands, any of you registered for 412? Okay, one person. So it'll be most helpful for you to review, so I do encourage you to check it out. So in the previous lecture, we covered PCA, autoencoders, and matrix factorization. And all of these were unsupervised learning algorithms. So we took each data set that we had, some X that lies in R n by D, and we mapped that onto some low-dimensional representation of that original data. And we did that mapping based on preserving some salient characteristics of that data. And so these approaches made sort of this interesting assumption that data depended on some latent variables that are never observed. And so in the context of matrix factorization, those latent variables for the movie case could be things like the genre of the movie, how much action it had. And we never directly observed those, but what we wanted were machine learning models that could automatically infer that from the observations that we had, which in the case for matrix factorizations were the ratings that each user gave to each movie. And so today, we're going to talk about a different kind of unsupervised learning, which is an algorithm for clustering. So for those of you who haven't heard this word before, clustering, what it means is to group data or data points into clusters. And so what we're going to do is reformulate this problem of clustering as a latent variable model and learn that model using the EM algorithm. But we're going to start very simple first, which is the k-means problem. So the problem is as follows. Let's say we have some n by d matrix that's given to us by a user. Our goal is to find clusters within this matrix. What exactly is a cluster? A cluster is a group of points that exhibit similarity to one another and exhibit some notion of dissimilarity to points that are not in the same cluster. So what is the output of a learning algorithm that solves the problem of clustering? It might look something like this. It might look like taking the rows of this matrix and finding groups of rows such that all of those rows belong to the same cluster. So what we might want to get as an output from this algorithm is that the first set of rows all belong to the cluster k is equal to 1. The next set of rows all belong to the cluster k is equal to 2, and the third set k is equal to 3. So that is what we're going to get as the input and the output from a clustering algorithm. And so sometimes the data form these clusters where samples within a cluster are similar to each other and those in different clusters are dissimilar. And we call this data coming from a distribution that is multimodal. And so here the word multimodal means data that has multiple modes. So in the context of a probability distribution or the mode thereof. So when a distribution has multiple different modes, it means the PDF of the distribution has these peaks. And whenever you have a peak in the PDF, you're going to get lots of different samples. And when the locations of those peaks are different, we say that the distribution is multimodal. And so here's an example of a distribution that we're going to sample from and observe the samples in 2D. And so this underlying distribution is multimodal, because as we can observe here, you might note that this has at least 5 different modes in the density, just looking in 2D at these samples. So let me pause here to see if folks have any questions about the idea of a distribution being multimodal, or what it means to identify what these kinds of modes are with an algorithm like clustering. Okay. And so if we had this data and we asked, this was our data set that was in our matrix X, what might be a reasonable clustering assignment for this data set? Then I think visually, if you or I were to look at it, we might say, well, I think that there's 5 clusters here. I could group all the data from these points into one cluster, these points into another cluster, these into a third, fourth, and fifth. So I think K is equal to 5. And these are the identities of how the observed data split across all of the clusters. So this might be a potential output from a clustering algorithm that is run on this 2-dimensional data set. So this is an unsupervised machine learning technique because we don't get access to any labels whatsoever. We're only given these points. And our goal is to identify what the cluster identity of every point is. And so what's the intuition here? Well, each point, assume that we have K clusters, and that each point is close to its cluster center or its cluster mean. What does this mean? When we say mean, we mean the average of points within the cluster. So in the previous visual example, we can denote the representation of a cluster as the average of all of the points that lie within that cluster. So if we have 5 clusters, we can take all the points within a cluster, take the average of those vectors, this is in 2D, and just visualize what that mean is. And that would give us these 5 points that I've drawn on this board. So these are the means of the clusters. So how do we actually find this and solve this problem? So we're going to make use of 2 ideas. The first one is that given the cluster assignments, we can easily compute the cluster centers. So how do we do that? So if I gave you the cluster assignment for every point, which is to say for each of the n points, I told you which cluster it was in. How would you compute the cluster centers? Yeah. That's right. So you would, so let's say they had K clusters. For each of those K clusters, you would go through and collect all the points in your n samples that were within that K cluster, and then you would average those points to get the mean. And then you would repeat that for cluster 1, 2, 3, 4, 5. So that's how you get the cluster means. So now assume that the means are fixed. So someone magically gave you the cluster means. They gave you the location of all of these centers. And now your learning goal is to figure out for each of the points, for each of the n points, which cluster it belonged to. How would you solve that problem?
You see which mean it's closest to.
You're right. So all you're going to do is draw a line between a point and all the cluster means. And you might assign this point to the cluster center that it is closest to. And you would repeat this process across all of the n data points that you have in your data set. And that's how you could get the cluster assignments. Now the problem here is that we know how to solve it given one, how to find the other, and vice versa. But we're never given both simultaneously. So this represents this chicken and egg problem. And so we're going to use a simple heuristic. We're going to start randomly, and we're just going to alternate between these 2 steps, step 1 and step 2. So we're going to randomly pretend that the cluster centers are in some n-dimensional space. We'll pick 5 random points, and then we'll repeat between finding the cluster assignments for each point and then refitting the centers. So let's look at what that means visually. So we're going to randomly initialize the cluster centers and alternate between two steps, the assignment step and the refitting step. So in the assignment step, which is this first slide here, we're going to assign each data point to its closest center. So we've randomly initialized the cluster centers here. So we have three centers, green, red, and blue. We've randomly initialized them. And for every point, I'm going to try and find out which cluster mean that point is closest to. Once I've found whatever that point is, whatever that cluster mean is, I'm going to assign this point to that cluster. So these 2 points end up getting assigned to this red cluster denoted by this edge. These 3 points get assigned to the blue cluster denoted by this edge. And these 4 points get assigned to the green cluster denoted by these 4 edges. So that is the assignment step. Now that I have associated with each data point a cluster center, I'm going to run the second step of my algorithm, which is the refitting step. So the refitting step is just going to, as your colleague mentioned, take a look at all of the points that were allocated to a single cluster. So in this particular case, I'm going to take a look at these 4 points allocated to the red cluster, and then I'm going to move the location of the cluster mean. So I'm going to recompute what the average of these points is, and I'm going to use the new average, and I'm going to set that to be the new cluster mean. So whereas my previous green point might have been somewhere here, I've now moved it after the refitting step all the way here. Similarly, my red point might have been somewhere here. After the refitting step, it gets moved up here. And the same happens to the blue point. So any questions about what's going on visually in this slide in terms of what these 2 steps are actually doing? Yes? Does the assignment step go through all data before going through refitting? Yes. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 points. We're going to go through all 9 points, assign them to clusters, and then move on to the refitting step. Yes?
So these red, blue, green points are not actual data points, you're just saying them.
They're just, we'll talk about how to represent them, but for now you can think of them as something outside the data. So, but they are real points. In that we're going to have a parametric representation of them, but they're not in the original data set themselves. There are scenarios where at some point in these 2 steps they could coincide with one of the points, but that would be chance and not something that you would plan for.
Okay, we just keep refitting that like new point that we made. So we're not like in the refitting step, we're not like looking at the 4 points in the cluster and being like which one of them should be the mean.
Correct. We're not doing that. We're moving this new representation of the mean to a new location. Yes?
At what point would we be adjusting like the number of clusters
Good question. So we've sort of started here by assuming that the number of clusters is 3, and we'll talk about how we set that, but in practice, the number of clusters is a hyperparameter to this unsupervised learning algorithm, much like we do it for PCA. Yeah? Yeah?
So does that mean that like how we set the initial set of cluster also
How you set the initial point is, it's not a hyperparameter, but it is a random initialization.
But like if, for example, if you initialize one centers into like very left top, and then you will like no matter how you fit it, you will still be around that region.
We'll talk about what are some worst case pathologies that could happen from random initialization and how to solve that in about a few slides. Yeah. Yeah.
Does the number of clusters stay constant throughout this algorithm?
Yes. So once it's a hyperparameter of the algorithm, which means once you set it at the beginning, it stays constant. So at the end, you will only get out the identity of these 3 cluster means and the assignments associated with which point is assigned to each of them. You had a question?
What if now the points are assigned to a cluster?
That would never happen, because in the assignment step, we would go through all of these points and pick one of these 3 points. If that's the closest mean that's really far away, then that's what it's going to be assigned to.
There could be a mean that is not the closest mean to any point.
But what does close mean? Like, as long as you can compute distance, it's just a large number, right? And as long as that number is smaller, so let's say if this was 1,000, if this was 2,000, and this was 3,000 in L2 distance,
I mean, all the points are assigned to some cluster, but if a cluster means that it's not associated to any point,
that wouldn't happen. A cluster mean is always going to be associated to one point, because at the end of the assignment step, every data point is going to be associated with a cluster mean. Because remember, this is an algorithm you design. So we're going to design it so that we're going to make these lines representing annotations of which cluster mean every point is associated with. Yeah.
I might be wrong, but I think what he means is, let's imagine that two points that are connected to the red one was connected to the green one instead. How would we move around that red cluster mean? It had no points connected to it.
So you mean to say that what happens if instead of the red being here, it was here in two-dimensional space,
yes.
and therefore it had no points associated with it?
Yes.
Okay, sorry, I misunderstood understood your question. So if you initially have no points associated with it, then you can effectively, what will essentially happen is that you will have no assignments in the first step. But if after the second step in this refitting stage, some of these means move further away from these 2 points, there could be a point in a future assignment step where this becomes the closest cluster mean, at which point it will have points allocated to it. So you're right that there could be a period of time in this algorithm where it does a single cluster center may not have a certain set of points associated with it, but there's no guarantees here. Like, at some point in the future, the cluster means could move away to enough of a degree that this red cluster center gets connected.
If that could happen, but if in the end it doesn't happen, then we are less cluster than we want to have.
If it doesn't happen, then you do have less clusters than you want to have, and we'll talk about that as a pathology in a few slides as well. Yes, one more question, then we'll move on. So we'll talk about the relationship. We'll answer that question essentially in the second half of the lecture. Okay. So we should move on. But I want to show you a visual example of what could happen in the context of clustering, particularly two-dimensional data. So if we walk through this example, you have this set of two-dimensional points, and you start out with these two as your cluster centers. And so you will carve up your data set in a manner such that all these blue points are associated with this cluster center, and all these red points associated with this cluster center, and then you'll run the refitting step. So you'll move the cluster centers to their new location. So this X, which was previously here, now gets moved here, and the X that was previously here now moves here. And then you'll repeat the assignment step. So you'll throw away the old assignments, and then you will rerun assignments. And so now this time, anything to the left of this line gets associated with this cluster, and anything to the right of this line gets associated with this cluster. And you'll keep repeating these two steps until you get to a point, and this is your convergence criteria, that the cluster assignments do not change and the cluster means don't move anymore. So that's basically the algorithm. So now let's take that intuition and turn this into mathematics. So what are the parameters that we need for the k-means learning algorithm? In order to be able to instantiate what I talked about before, you need two things. The first thing is what we'll call this responsibility matrix. And this responsibility matrix is an n by k matrix. So it's an n by k matrix where there's one responsibility vector associated with every data point. And each entry of the responsibility matrix, so each row, is a one-hot vector. It is a one-hot vector of dimension k, such that the entry of the matrix k or the entry or the column of where there's a 1 in this row vector is what tells you which cluster this point is associated with. So that's what the responsibility matrix is. The other set of parameters that we have for this algorithm is this matrix of means. So this is a k by d matrix, and a k by d matrix where each row, mk in Rd, represents the mean of the kth cluster. So those circles that we're seeing before, or those x's, they're going to be represented in this matrix of means. And so we'll use m sub k to denote every row of this matrix of means, and we'll use Rn to denote one of the entries of the responsibility matrix. So any questions about these two matrices? Okay, so now let's dive into the mathematical formalism of what we're actually doing. When we solve the k-means objective via alternating between those two steps, you should ask, what is the objective function that you're actually trying to solve? Because like all machine learning algorithms, there exists some objective function. And in the k-means objective, we are attempting to find the cluster centers M, so the entries or the rows of that matrix of means, and the assignments R, so the rows of the responsibility matrix, that minimize the sum of square distances of data points to their assigned cluster centers. So what we want to do is search over these rows of the matrix M as well as the rows of the matrix R in such a way that every point gets assigned to a cluster center, and the average distance that a point is assigned to a cluster center is minimized. So we want to find cluster centers such that they're organized spatially so that the sum of square distances is minimized. So let's break apart this cost function. So we have some cost function j of mr, and we want to minimize that cost function. So this is a min over mr, a summation over the endpoints, and a summation over the k clusters of r sub k multiplied by some distance metric, which in this case is the squared distance metric, the L2 norm. What is inside this distance metric? It's the distance between mk, which is the cluster center corresponding to the responsibility entry for the kth cluster for point n, and xn. So this term can take two values. It is either going to be a 0 if x is not in the kth cluster. So if x is not in the kth cluster, then this r term is going to be a 0. And so this term doesn't matter. But if x is in the kth cluster, and remember, Rn is a one hot vector, so it can only be in one cluster. If Rn is in the kth cluster, then this term will be the distance between xn and that cluster center's mean. So that's how you would interpret this equation. So the first term here is the distance between xn to the kth center, and this second term is going to be 0 if xn is not in the kth cluster, and it's going to be the distance, whatever this distance is, if xn is in the kth cluster. And we're going to sum all of that up over all the data points. And that's the cost function that we want to minimize. And we want to minimize it subject to the constraint that Rn is a one hot vector, so that's what this constraint is telling you, and that Rn is also binary. So every entry of the responsibility matrix is either a 0 or a 1. So any questions about the k-means objective function? Yeah?
Is this like a linear program?
It is not a linear program because you have two things you're optimizing over. And at least in the second term, it's quadratic. Yeah. So you could be affected by the curse of dimensionality insofar as you have a measure that depends on the distance. And distances in higher and higher dimension are affected by the curse of dimensionality. Okay, and so finding the exact optimum of this optimization problem, the joint minimizer of M and R, can actually be shown to be NP hard. But moreover, k-means can also be seen, the algorithm that we talked about, as performing block coordinate descent on this objective. And so the assignment step is minimizing with respect to Rn, and the refitting step is minimizing with respect to Mk. Because recall what we said was the assignment step was that we were trying to find the assignments R. We were trying to find which point, which cluster center every point was allocated to. And we will show in the next slide that that corresponds to minimizing this objective with respect to R. And in the refitting step, we were updating the means. And we'll show why that corresponds to minimizing this objective with respect to M. And this alternating procedure of alternating between the optimization over R and the optimization over M is an example of what's called block coordinate descent. So how many of you have heard this phrase before, block coordinate descent? Okay, how many of you have heard the phrase coordinate descent before? Okay, so whenever we think about doing, so this is a phrase that you will see in the context of numerical optimization. Whenever you are minimizing an objective, let's say in many of the examples we saw before, we were minimizing the function corresponding to the loss with respect to some parameters using gradient descent. We were updating all of the coordinates at once when we did gradient descent. And that's an example of doing coordinate descent in the context of the set of entire coordinates that you have, because we were updating all of the parameters at once. Whenever you see the term block coordinate descent, it means that your optimization procedure is not doing everything all at once, but rather it's splitting up the optimization into two steps. It's first performing optimization over the R's in the assignment step, and then it's performing optimization over the M's in the refitting step. So if you take the parameters of k-means, the R and the M matrices, and you turn them into a giant vector, then this algorithm is going to be updating blocks of this vector at each step, and that's why it's called block coordinate descent. What is another example of block coordinate descent that you've seen from one of the previous lectures? Someone must know the answer, yeah. Batch gradient descent is still updating all the parameters of the model, right? It's just changing the number of examples you're using to compute the gradient. Yeah. That is so in the project you have to update between the theta and the beta values. That's an example of block coordinate descent. Yep. Yeah, but that's still coordinate descent, because that weight vector is treated as one giant vector in the parameters of your model. So think back to matrix factorization, the algorithm alternating least squares. That's an example of block coordinate descent, because you are first updating the set of factors corresponding to one matrix, then you're holding it fixed and updating the other matrix. So it has this property that you change one block of parameters at a time. And so to see why alternating minimization is minimizing that objective, let's look and break apart that objective function in the previous page into two steps. We're going to fix the cluster centers mk. And so if we fix this term with respect to this objective function, this is just a constant. And so we're basically choosing these Rn's, and we can choose them independently for each of the n samples that we have. So we can choose the responsibility vectors n, Rn, for each of the rows of that responsibility matrix independently. And for each row, we're minimizing the summation over k, Rn sub k, multiplied by this constant. So you get to figure out how to set your responsibility vector in any configuration that you want, such that this cost function is minimized. So the way you would do that, because you know that the responsibility vector is a one hot vector, the only thing you get to manipulate is where you put the 1. So where do you put the 1? What's the best way to put the 1 to minimize this cost function? It's to put the 1 in the location where the distance between xn and mk is as small as possible. So we're going to find the point in the vector, the location k, that minimizes mj minus xn norm squared, and we're going to do an arg min over j, so that's going to give us one of our clusters k. And for that choice k, we're going to say that Rn sub k is equal to 1, and it's 0 otherwise. And so this ensures that xn is assigned to cluster k hat, and exactly and only one cluster k hat. So any questions about the solution to this minimization problem? This, by the way, is a linear program, but it's just a very simple one, so you can read off the solution. Okay, next, we're going to look at how we update the cluster means. If we fix the assignments Rn, then they can easily find the optimal cluster centers. And the way to see that is that we're going to take this equation and we're going to take the derivative with respect to ml for some choice of L. So we're going to take the derivative and set it to 0. And remember this, whenever you see a norm squared, you can write it as mk xn transpose mk minus xn. This is a vector dot product. The derivative of a vector dot product with respect to one entry here is 2 times mk minus xn, which is how you get to this answer here. And then you just set this summation to 0. Because when you take the derivative with respect to dml, you only choose one of the terms in this kth summation, which is why it goes away in the derivative. So you're left with Rn sub L times ml minus xn, which is the actual value of the derivative. And setting it to 0 gives you that ml is equal to the summation over Rnl xn divided by Rnl. So let's see what these terms actually mean. The summation Rnl is basically the number of points in cluster L. Because what we're doing is, this is the responsibility matrix. We're summing over the n rows of the matrix and looking what's happening in the lth column. And the responsibility matrix is a one hot matrix. And if there's a 1 in one of those columns, it means that there's a point here. So by summing over the rows for a single choice of columns, you're counting the number of points in the lth cluster. So that's what this denominator is. And the numerator is the sum of the vectors that lie in the lth cluster. So it's taking the 1s here, and it's multiplying the 1 with the original vectors. So we're going to sum up in our original data matrix only over the points that lie in the lth cluster. And you put these two together, and you get that this is basically computing the average of the points in the lth cluster. So that's how you solve this optimization problem and show that k-means alternates between minimization with respect to assignments and centers, and that this is an example of alternating minimization or block coordinate descent. So in terms of putting this algorithm together, the algorithm is pretty simple. You set your k cluster means to random values, and you repeat the two steps, the assignment step, which optimizes with respect to the responsibilities at each point, and the refitting step, which optimizes that objective with respect to the cluster means, and you set them to the solutions we just derived. And do this until convergence, which is to say that the cluster means don't change and the cluster assignments don't change either. So we can say a few things in terms of why this algorithm converges. The first reason is that we know that each step of the k-means algorithm is strictly going to reduce the overall cost function that we have. So if we were to plot the cost function as a number, as a function of each step of the k-means algorithm, it is a monotonically decreasing function, or it's rather monotonically non-increasing. And the reason why is because we just showed that we're solving the minimization problem in this block coordinate descent manner. Next, we know that if the assignments don't change in the step, there exists a point at which we will have converged, which is to say somewhere between point 0 and point infinity is a point where the assignments don't move very much, which indicates that there exists a condition that we can use to stop the algorithm. And the third step that you need is that convergence has to happen after a finite number of iterations, because the number of possible cluster assignments to points is large, but it is still finite. So these three arguments provide evidence of why the k-means clustering algorithm will actually converge. But at the end of the day, it is a local heuristic-based optimization to this otherwise non-convex optimization problem. And so the objective J is non-convex, and coordinate descent on J and block coordinate descent is not guaranteed to converge to the global minimum. And there's many instances for k-means to get stuck in local minima. So one might be, as your colleague pointed out, it could not use all of the clusters, so that could be a bad local minima. Another might simply be the situation that we have here. If we ignore all of the cluster centers here and ask a human being how many clusters do you think there are, can you associate them with these points, they might say, I think these 4 points are in one cluster, this is in one cluster, and this is in another cluster. But what this example is showing you is that if you initialize your first cluster mean to be the midpoint between these 4 points, and the second and third to be the midpoint between these two and these two respectively, you can create an assignment that ensures that the next update step for k-means will not make any difference. So this represents a bad local optimum to the objective function of k-means. And so k-means has a really simple idea, but it's been used a ton across machine learning. And so in this particular case, you're going to run k-means and replace each pixel by its cluster, and this enables you to do very, very simple forms of segmentation. Given image pixels, you can use k-means to identify superpixels, and so that enables you to do coarse or fine-grained granularization of image data. But in reality, it has a ton of interesting use cases, both across the sciences and social sciences and economics, etc. So it's a really important algorithm to know how it works. But one of the limitations of k-means is essentially that that every point has to be associated with one and only one cluster. And in some cases, you might be interested in a scientific problem where a point can be associated with multiple clusters. You might want to have an algorithm that gives you the flexibility of discovering not just the single cluster that a point is, but potentially mixed membership of points to clusters. And so that introduces the idea of, rather than making hard assignments of data points to clusters, we can make soft assignments. And so one cluster might have a responsibility of 0.7, while another might have a responsibility of 0.3. What does that mean? So previously, if we had two clusters and we had point n, we had Rn, that might be 0 and 1, indicating that this point was in cluster 2. What the sentence is saying is that we could alternately imagine an algorithm that gives us 0.7 and 0.3, indicating that this point xn is mostly in cluster 1, but also has a small chance of having come from cluster 2. And so that's what it means to have soft responsibilities or soft assignments of data points to clusters. And this allows a cluster to use more information about the data in the refitting step. And so the learning algorithm for soft k-means is a very simple modification of the original k-means algorithm, and that's what we'll talk about in a bit. But there exists a modification that we need to make. And so the modification that we need to make is going to be very similar to the ideas that we talked about in the context of multi-class classification. So think about multi-class classification or softmax regression, where we talked about the idea of printing out a probability distribution over k things, k classes. When we wanted to get a probability distribution over k things, we used the softmax function. So the softmax function, remember, is very simple. If we had a vector z1 and z2, what we would do is we would do e to the z1 divided by e to the z1 plus e to the z2, and this would be e to the z2 divided by e to the z1 plus e to the z2. So that's what the softmax operation actually did. It exponentiated every data point, and then it renormalized the resulting vector so that we had a vector that summed up to 1. And so in the context of soft k-means, the algorithm is as follows. We're going to change the assignment step now so that we set our n to be the result of x of basically the softmax operation applied to negative beta times the distance between mk and xk. And so after we do that step, what we're going to do is the refitting step where we're recomputing the means. But instead of selecting the data points n within each cluster, we're basically going to sum over all of the data points that we have, and we're going to multiply by each data point the responsibility that that cluster has for that data point. So we're going to get a convex combination of data points in the numerator, and the denominator is still going to remain the total responsibility that this cluster has. So you'd get some weighted average of points rather than just the average of points within that cluster. But before that, there's a really important idea to understand in the context of soft k-means, which is why do we multiply by negative beta? So just as a show of hands, anyone have any ideas on this? Yeah. Beta is a constant. So do you know why we multiply by negative beta? Okay. Yes? Say more. Okay, so let's say we have a point x, and this is our xn. All right? You have an idea?
Yeah, I was just going to say that if you take the distances and square them, you're going to get really large values. And if you take e to the power of those values, it's going to be like really out there. But if you take the negative of a large exponent, then you're going to get really small values inside each of your softmaxes. So it's going to be nice to work with.
So it's not just nice to work with. So you're absolutely right that that's the numerical thing that will happen when you do e to the negative of this value. But could I just multiply, if my only concern was numerical optimization, couldn't I just multiply instead of negative beta? Can I just not multiply it by 0.01 uniformly? Wouldn't that have the same effect? So this negative beta is doing something a little more specific than that. Not quite. So let's think about this example together, because it's actually important to know why this is the case. So let's say we had a data point x, and we had 3 cluster centers. We had the triangle, the circle, and the star. Looking at this plot, which cluster should have the highest probability of this point being assigned to? The star, the triangle, or the circle? Like which of these clusters should have the highest responsibility? Yeah, the star. So we think that this should have the highest, and then this one may be a little bit less, and this one the least. Okay, so now that we have an intuition of what we want, let's look at what happens when we compute the distance vectors. So we're going to first compute the distance vector between this point, and that's going to give us, I'm going to make some numbers up here. So that's going to give us a 5. So this is for the star, that we have a distance of 5. I'm going to compute the distance here, and for the triangle, I'm going to get a distance of 10. And then I'm going to compute the distance to the circle, and I'm going to get a distance of 100 to the circle. So let me ask again, why do we multiply by negative beta?
Because it gives us like the reversible we want.
Exactly. Because what we want is that we want to put a high probability when we have a small distance. And what the negative beta does is that it lets us both flip the sign of these numbers as well as control how much we care about, to the point about numerical precision. And so when we multiply, let's say beta is equal to 1, then we get -5, 10, -100. And now when we apply this through a softmax operation, we might get something like 0.8, let's say 1.5, and 0.05. And this represents the intuition that we want, which is that the closest cluster center should take the most responsibility for the point that's next to it. So any questions about this idea of using and multiplying by negative beta the vector of distances and then running the softmax to compute the responsibilities? Yes? So good question. Why multiply it by another beta again? And so one reason to think about multiplying it by another beta is that we might be able to manipulate this equation that we get to be sharper or more dispersed. So if beta is very, very large, we can actually change this so that this becomes 0.99, and this becomes 0.001, and this becomes 0.099. And beta is what controls the strength of how close this softmax operation is to the deterministic setting of having hard responsibilities between cluster centers and points. And so how do you set beta? In part, it's typically a hyperparameter, but as I mentioned, as beta tends to infinity, you can actually show that soft k-means becomes hard k-means. So if you pick beta to be very, very large, you can, it's a simple exercise, and to show that exercise, I'll tell you what you'd have to do. Write down that softmax equation for the case for k is equal to 2, and take the limit of that equation as k tends to infinity. A trick that you might have to do is to move beta into the denominator of the exponent for the limit to be easily computable. But once you do that, you should be able to show that this statement holds true. And finally, there's another issue which your colleague mentioned at the beginning, which is how do you address clusters that have equal weight and unequal weight and width? Which is to say, if you have data points that, if there's a cluster that looks like a circle here, but then another cluster that looks like a giant ellipse here, you might still want all of the ellipse to be in one cluster rather than them being cut up into 3 or 4 different circles. How do you actually do that with a clustering algorithm is what we'll talk about next. So any questions? Yeah?
I don't know if I'm missing the point of this, but I feel like using soft k-means, if anything, is like counterproductive, because if you initialize if your random choices of means at the beginning is good, like k-means is going to make it converge faster to the correct point than soft k-means, and if it's bad, it's not like it's going to help you correct it. So I don't really understand that.
So the point of soft k-means is that you may be working in a domain where an individual wants to get an estimate of, for example, here's one use case for soft k-means where you talk to someone and they're like, I want clusters, but I also want how certain you are about these clustering assignments. And if you want some notion of certainty about clustering assignments, you can use these responsibilities as a proxy for certainty. But you're right that they serve fundamentally different tasks and might have very different local optima in their behavioral patterns. Any more questions about soft k-means? Okay, so what we're going to do is we'll take a 3-minute break and come back at 2:07 to talk about Gaussian mixture models and learning them with the EM algorithm. Like held out accuracy as a proxy for your decision making. So you can say, we tried these 3 things. This had the highest held out accuracy, and give a number, and that's why we chose it. Held out accuracy for like whatever downstream problem you care about. Or like, I'm using accuracy as a metric, but there could be others. So we should get started. I'm happy to take questions at the end. Sorry, yeah. Okay, so let's get started again. What we're going to do is think about the case of how we can do clustering with data that just doesn't, look like these nice blobs and circles that enable us to use k-means and soft k-means. So what happens when data does not look like a spherical blob? What if it's an elongated cluster? Or what if it's discrete data? How might we handle those two cases in the context of clustering? So the remainder of this lecture is going to formulate clustering as a probabilistic model. So remember, we've talked about a few kinds of probabilistic models before in this class. So the first one we introduced was naive Bayes, which was a generative classifier. The next one we introduced was Gaussian discriminant analysis, and we studied how various choices within that probabilistic model could help us solve different kinds of problems. For this lecture, we're going to specify assumptions on how the observables relate to these latent variables. And so we're going to use an algorithm called EM to approximately maximize the likelihood of the observed data. And this is going to enable us to generalize clustering to non-spherical centers or to non-Gaussian observation models. And so let's think again about the generative Bayesian classifiers that we're familiar with. And in the prediction case, what we had were two numbers, the prior probability of the class label and the conditional probability of the data given that class label. And we were doing maximum likelihood estimation to fit these two sets of parameters for both the prior as well as the conditional likelihoods of the data. And so we fit P of t and P of x given t using labeled data. So that's what we did for naive Bayes, for Gaussian discriminant analysis, and all the other variants thereof that we discussed. What we want to do now is consider the case where t is not observed. So if t is never observed, what we're going to do is call it a latent or hidden variable, and we're going to denote it with z instead. So the things that we can never observe are going to be denoted in z, and the things that we do observe, x, are going to be called the observables. So if we have a scenario where we have a latent variable, we can ask what is the probability density function that controls how the observed data actually behave. To obtain that, to obtain P of x, we can obtain that by taking the joint distribution and marginalizing out the hidden variable or the latent variable. So remember, this is just a generic rule of probability distributions, which is that if you have a joint probability distribution between x and z, you can obtain P of x by marginalizing out the latent variable. And so you can simplify the joint distribution by placing an assumption over how the observed variables relate to the latent variable. And in this particular case, we're going to pretend that there exists some latent variable z, and that the observed variables x are a function of that latent variable z. And so we have P of z, which is the prior distribution over that unobserved latent variable, and P of x given z, which is the latent variable conditional distribution for the observed data. So this is called a latent variable model, and it'll be the simplest form of latent variable models that we have in machine learning. So it's really important to understand it. And if you're really interested in studying them further, if you go on to take CSE 412, this is the primary topic of study. So the learning algorithms and the inference algorithms for latent variable models are what you will focus on in CSE 412. Okay, so this is a latent variable model. If P of z is assumed to be a categorical distribution, then this latent variable model has a specific name. It's called a mixture model. And different values of z are going to correspond to different components. So remember from your probability classes, a categorical distribution can be represented by a vector of size k. Each element is pi 1 all the way to pi k, is a number between 0 and 1, and we know that the summation of all the pi k's equals 1. Each number represents the probability that that variable, that random variable, actually lies in element k of this categorical probability distribution. So that's how you would interpret the parameters of a categorical probability distribution. So before I go forward, any questions about what I've said on this slide? Yeah.
Yeah, so I don't really get, so not every single
So,
What if they don't correspond?
so the probability distribution of x given z is basically telling you that if someone magically gave you the observed distribution, sorry, if someone gave you the latent distribution, then conditional on knowing what the latent variable is, you can characterize the distribution of the observed variables. That's what P of x given z is giving you. And again, these are just assumptions that are made. So remember, in probabilistic modeling, what we do is we come up with some magical setup that we believe the world of data obeys. Remember, in naive Bayes, we made these silly assumptions that everything was conditionally independent. And we knew that assumption wasn't true, but we made it, and it was still a reasonable model. And so again, we're going to make this assumption here. We're going to make the assumption that the probability distribution of the observed variables is controlled exclusively by some latent unobserved process that you don't get to observe. And if you had access to that process, then you could characterize what the conditional distribution of the observables looks like. So that's what P of x given z is. And that unobserved process has some prior distribution, and that's what P of z is. Any more questions about just the setup for latent variable models? Okay, so now we're going to start putting distributions to each of those probabilities. When P of z is a categorical distribution, and P of x given z is a Gaussian distribution, the resulting model is called a Gaussian mixture model. And the reason it's called a Gaussian mixture model has to do with what the probability density function for the observed data looks like. So I'm going to take my equation here. I know that this is a categorical distribution, so I can represent that with pi k. And I know that this is a Gaussian distribution, so I can represent that as a Gaussian with some mean and some covariance matrix. And when I substitute that in, I get this equation here. So let's stare at this for a while. This is basically a convex combination of a number of k different Gaussian distributions, because each of these is a number between 0 and 1. And they all sum up to 1. So it's a convex combination of Gaussians. And that's why we call it a mixture of Gaussians. So up until here, any questions? All we did is we put in specific choices of distributions for P of x given z and P of z. And when P of z is a categorical distribution, the resulting class of models is a mixture model. And in this case, since it's Gaussian mixture model. So if, for example, our conditional distributions over the observables were modeled with an exponential distribution, it would be a mixture of exponentials. Okay, so pi k are called the mixing coefficients, and the summation over pi k over all k is equal to 1, and each pi k is greater than or equal to 0. And so this is going to be something that defines a density over x. So we can fit the parameters of our model using the maximum likelihood principle that we talked about in class before. We're going to try to match the density of the observed data as closely as possible to fit the parameters of this model. What are the parameters of this model? We have pi 1 all the way to pi k, we have mu 1 all the way to mu k, and we have sigma 1 all the way to sigma k. These are the sets of parameters of this Gaussian mixture model. And so there's lots of known results showing that GMMs are universal approximators of probability densities, and the intuition behind them is essentially you can represent any density via a mixture of infinitely many things. So as you set the number of mixture components to be very, very large, you start to get arbitrarily good approximations to any density. And so even diagonal GMMs are universal approximators. And again, we can write down this latent variable model via a generative process. So whenever you see the term generative process, you should sort of think of it as this magical story that you as a practitioner get to tell of how you believe the data came to be. It doesn't have to be the right story, it has to be an approximately good story. And so in this case, the approximately good story that is being constructed by the machine learning practitioner is that each data point is independently first queried as to which mixture component it came from. So for each data point, we're going to first sample from this categorical distribution over our prior, and we're going to pick one of the categories. And once we've selected the kth category, we're going to use the mean and the covariance parameter for that category to sample the data itself. So think back to that example of 2D data points that lay here, here, and here. And so in this particular example, in this 2D data set, this generative process for this particular data point was effectively that first someone picked k is equal to 2, if this was k is equal to 1 and k is equal to 3. So for this data set, first zi was sampled to be the value 2, and then xi, whatever it is, was sampled from a Gaussian distribution with mean and covariance 2. So that's what these equations are telling you. Any questions about the generative process of this data? Okay, so given any two-dimensional data set that you believed was samples from a mixture of 3 Gaussians, you can start thinking of how best to visualize what this data looks like. So if you look at just samples from P of x given z, how would you do that? You would first set z is equal to 1, and then you would sample points from it. Then you would set z is equal to 2, sample points from it, z is equal to 3, sample points from it. And that's what these 3 sets of points actually are. So let's say that's what you got. That's your data. If you look at samples from the marginal distribution of P of x, then you are effectively ignoring the fact that you're marginalizing out over the cluster structure or over the component identity for these points. So that's why they're all coming from the same pink set of points. And the third quantity is what we call this responsibilities, this P of z given x. Yeah.
Sorry, just recall, what does the z represent again?
So z represents this latent identity of which component this point came from. So if I gave you this data set, and for any given point, I can ask which of the 3 components did it come from. And according to, because I have a mean and a covariance for this cluster, I have a mean and a covariance for this cluster, and I have a mean and a covariance for this cluster, I can evaluate what P of z given x looks like for each of those 3 components. And what I'm going to do is I'm going to color, and the intensity of the shade of this color is going to correlate with the strength of the probability that it came from cluster 1, which is why these are deep red, and these are a mix between green and red, or cluster 2 or 3. So that's what these 3 plots are visualizing. So all of that is really just set up, because our ultimate goal in the context of this class is really to learn how we would choose the parameters mu k, sigma k, and pi k. And so the maximum likelihood principle tells us that we should choose parameters to maximize the likelihood of the observed data. And so the problem here is that if we look at the likelihood of the data, we don't actually know which clusters points actually came from. So we don't observe the cluster assignments z, because the only thing we observe are the data x. So log p of d is equal to a summation of log p of xn, because each point is generated IID. And now for log p of xn, we can look at what happens. So we can always find p of xn by marginalizing out z. But we don't actually know what identity is associated for each data point. And so the visualizations for fitting a mixture of Gaussians in one dimensions kind of looks like this. So if you had this data and you fit a single Gaussian, you might get this as your fit. But if you fit 2 Gaussians, you would get these 2 peaks. And the same is true in 3 dimensions. And so the learning challenge that comes about as a consequence of this problem is effectively that we're running into knowing what the data is, but not knowing associated with each point which cluster it actually came from. So we set out by saying we wanted to learn this latent variable model. In this latent variable model, every point is first generated from one of the components, and then conditional on the component's parameters, you sample that data point. That's the generative process for this data. In practice, you want to learn the parameters of these models, but what you have are the data itself. You know that this data came from this mixture of these k different Gaussians being mixed together. You don't know what the mixture components were. You don't know how much of each Gaussian distribution existed in your data, and you don't know the parameters of those Gaussians themselves. And so the learning problem is how do you fit those parameters of your model? And so what we're going to do is, using shorthand notation, let theta be all of the parameters that you want to fit. So these are your mixture components, the means and the covariances. And we're going to let x and z denote the set for all of the n data points of observables and latent variables. Remember, we don't observe this, but we do observe this. If we write down the maximum likelihood objective, which is the likelihood of all of the data points x, we get that it's a summation of log pxn, and each pxn is this summation over pi k times log p xi given zk, because this is the result of marginalizing out the latent variable. Now this is problematic, because this equation has no closed form solution. So you cannot use your trick of taking derivatives and setting it to 0 anymore. What's more, the solution is not identifiable. How many of you have heard the word identifiable before? Okay, so identifiability effectively means that you are trying to solve some kind of optimization problem, and there exists a bijection between the function or the solution of this optimization problem and the parameters that you find. Which is to say there exists uniqueness is one of the facets of an identifiable optimization problem. So there exists a unique solution to this optimization problem, but that's not the case here. So just as a question as to think about whether the optimization problem for a neural network is identifiable. Does there exist a unique set of parameters that all, actually to even ground it in something simpler, think about the problem of binary linear classification for the XOR data set that we did in class. Like for that problem, we constructed this neural network that was able to classify the XOR data set. But is that a unique solution to that problem? How many think it's unique? Okay, how many think it's not unique? Can someone tell me why it's not unique? Yeah.
There are multiple assignments of the weight.
That's exactly right. So you can like move the weights around between hidden units, for example, and you can get the same function that has the exact same output for the same set of inputs in a neural network. And it's the exact same thing here. So you have some mapping from your data onto the set of parameters. That's what all learning is. And so the solution is not identifiable because there's many ways for you to get the same likelihood number for that explains your data. And in this particular case, it's due to invariance in permutations. So what does that mean? If I had 2 Gaussians, so let's say I started out with 2 Gaussians, and the probability of those Gaussians was 0.7 and 0.3 and 0.7. And the means of those Gaussians were 1, 1, and 2, 2. So let's say the means and variances were 1, 1, and 2, 2. So this is scenario 1. In scenario 2, I have 0.7 and 0.3. And the means and variances are 2, 2, and 1, 1. So these are the parameters of my mixture of Gaussians in scenario 1 and scenario 2. My claim here to you here is that both of these scenarios have exactly the same value of P of X. And the reason why that's true is that it's because you can permute the identity of where the clusters lie between 1 to k without changing the likelihood function, which is why this problem is not identifiable due to permutation that exists. Yes?
Sorry, are you saying they can have like one solution where a certain distribution where most like k equals 3 and another where that same distribution where most k equals 2, or are you talking about something else?
No, I'm saying for a fixed choice of k, when you learn a Gaussian mixture model, I can come up with permutations of that solution, all of which have the exact same likelihood of your observed data. Because I can just swap the identities of the cluster means and the cluster proportions, the Gaussian means and the Gaussian proportions. And so another easy way, if you don't see that immediately, is to just think about the fact that P of X is a summation over these k things. And so it doesn't really matter if I sum the 0.3 first or if I sum the 0.7 first. And that's what these permutation symmetries are. So each of them represents a different solution, but they all represent the same likelihood function. And so if you're, there's lots of really cool mathematics that tries to formalize these permutation symmetries and many machine learning algorithms using rings and semi-rings, but that's much more in the realm of theoretical machine learning research. But you should know that that exists if that's something that you're really interested in exploring. So let's talk about a more practical question, which is how do you actually optimize this thing then? You run into the problem that this is non-convex. You also need to enforce non-negativity on your pi k's because all of them have to sum up to 1 and be greater than or equal to 0. And you have to also enforce this positive semi-definite constraint on the sigma k's. So direct optimization of this log likelihood function of the observed data is infeasible. So we need another approach. And the approach that we're going to take, what's more, there's also a learning pathology that you might run into if you attempt a direct global maximization of this objective, which is that there exist pathological solutions where you put all of the mass of one of the Gaussian clusters onto a single data point, and you send the variance to be a very, very small number, or the standard deviation. And because it's doing such a good job of explaining exactly one point, you will get a very high value for the likelihood of the data, while the other Gaussian is going to explain all of the other data points that you have. Yep.
How come we didn't have this problem when we did like discriminant Gaussian analysis?
In GDA, so yeah.
It looks very like similar, like factor.
Right. So in GDA, the main reason that you don't have this problem is you can actually write down the log likelihood of all of your observed data. And it had a really nice structure that enabled you to learn the parameters of the prior independent from the parameters of the conditional likelihood function. But here they're like coupled together in this really weird way. And that's what makes it very different from the GDA optimization problem. But it's a really good question to compare and contrast the two. It'll give you a lot of intuition for why learning in latent variable models is hard. And so let's think about the same trick that we applied with k-means. Let's pretend that we know the parameters of the Gaussian mixture model. So we're going to pretend that we know the parameters of the pi 1 to pi k, mu 1 to mu k, and sigma 1 to sigma k. If we knew these parameters, then we can actually infer which component a data point xi probably belongs to by inferring its latent variable zi. So if we had some configuration of the parameters of this Gaussian mixture model, we can solve for p of zi equals k given xi for every xi. How do we do that? We just apply Bayes' rule. So p of zk times p of x given zk divided by the summation over z equals L of p of x given zl. So we can evaluate what this probability is for each of the different choices of Z. So if you have 3 components in your mixture, you can evaluate what the probability of each of them is for any given data point, because you can take the assumed values of the parameters and substitute them in here. Because the first term would just become pi k, the second term would just become the evaluation of a Gaussian PDF at xi given mu, in this k, and sigma k. And just as we did for GDA, you could run posterior inference to infer what the identity of the latent variable was, if you knew the parameters of the model. And now, if somehow you knew the latent variables for every data point, then it turns out that this becomes a fully observed data set. So if someone magically gave you what the latent variables were for every single data point, then this reverts to the case of GDA. Because now everything is fully observed, it means the log likelihood can be written as the summation of log pzi plus log pxi given zi. And just like GDA at training time, you can run maximum likelihood estimation, set the derivatives to be 0, and get closed form solutions for the means, the covariances, and the prior probabilities of each of the different components of the Gaussian of this categorical distribution. So these are the maximum likelihood estimates, assuming that for each data point you knew what Zi actually was. So this should start to give you a flavor of what that learning algorithm is going to look like. Because we don't know Zi, and so we need to marginalize it out. And now that's what gives us this really awkward log likelihood. So the problem is that the log is outside the sum, so we don't have things that simplify. So we can't move this summation outside the logarithm here. And so just like before, we have this chicken and egg problem with k-means, and so we're going to do this alternating step again. We're going to pick some values of theta, which are the parameters of our model, and for the choice of parameters of our model, we're going to infer or run Bayes' rule to infer what the latent variable is, assuming that those parameters were actually true. Next, given the inferred values of those latent variables, we're going to update the parameters. So we're going to do maximum likelihood estimation on the parameters by pretending that our guess for what the latent variables were actually the true values of the latent variables. And we're going to do this in an iterative fashion. And this iterative algorithm is called the expectation maximization algorithm. So in the expectation step, we're going to compute the posterior probabilities over the latent variables given the current model parameters. And that's going to tell us how much do we think each Gaussian distribution generates a data point. And in the M step, or the maximization step, we're going to maximize the likelihood of the parameters of our model given the guesses that we had for the responsibilities of these latent variable distributions. So pictorially, here's what's happening. We first take a look at each data point. So we start off with these random guesses maybe for what the Gaussian parameters are for both the mean and the covariances that I'm going to represent with these ellipses. And then we'll assign for each data point a responsibility. We're going to compute the posterior probability that Zi is equal to the red cluster, the blue cluster, and in this case, the green cluster has probability 0 for this data point. And we're going to repeat that for this data point, for this data point, this one, and everything else. So a data point like this vector says that P of Zi is equal to the red cluster is about 0.5, P of Zi is equal to the green cluster is about 0.5, and P of Zi is equal to the blue cluster is very, very close to 0. So that's what this 0.5 and 0.5 mean here. And once we have these numbers for each of the different data points, we have the Zi's. And having the Zi's mean you can now simplify the log likelihood over all of your observed data as a summation over the likelihood over the observed data and the likelihood over the guesses. And for each of them, you can now update the model parameters based on these guesses. So that's going to move the mean and the variance of this red cluster from this oval to something that looks a little bit more circular because it's explaining these points. Similarly, this blue circle is going to be moved to something that's a little more ellipsoid. And that's what we do in the M step. And so EM for the Gaussian mixture models is basically going to assign the responsibility Rk of component K for data point I using the posterior probability. And we're going to apply the M step, which is to apply the maximum likelihood update. So we're going to guess what the responsibility for each point relative to each mixture component is. And then given those guesses, we'll use them to update the prior probabilities, the means, and the covariances for each of the Gaussian components. Okay. So what does this actually look like in practice? So as a practical use case, you can think of recording a bunch of temperatures in March in Toronto, both in Toronto and Miami, and you get data that looks like this. So you plot them, and this is your marginal distribution of P of X. And what you didn't record were which temperatures were Toronto and which ones were Miami. So you want to use a latent variable model to solve this problem, where you believe that this identity of the latent variable could be indicative of which underlying city a particular point actually came from. So that is a scientific problem that you might intend to solve with this. So you run the mixtures of Gaussians algorithm, and you start out with two Gaussians that look like this. And you're going to first start with the E step. So you're going to assume and use Bayes' rule to infer what the posterior probabilities are for each point. So every point here in this data set, you're going to try and evaluate, did it come from probability of z is equal to 0 given x, and what is the probability of z is equal to 1 given x, because there's two clusters here. And so you might write that down, and you'll get something that looks like this. And so this is plotting one of those two probabilities. So this is P z is equal to 1 given x, and perhaps this is the green cluster. And it's indicating that, you had your first Gaussian look something like this originally. What that posterior probability is indicating is that most of the points here are likely to have come from that cluster. So that's why we have a high value in this region of the space and a low value in this region of the space for the posterior expectation. And we're going to use this to now update the model parameters. So what we previously had were these two Gaussians. And now we have Gaussians that are a little bit more confident about which region of data they're actually trying to explain. And then we're going to rerun the E step, which is going to give us these two Gaussians after refitting the parameters. And we'll do this a few more times. So this is step 3. And by the time you get to step 10, you've basically, with a high degree of confidence, identified that this data set can be separated and modeled by a mixture of Gaussians in this manner. Okay, so any questions about the learning algorithm for mixtures of Gaussians? Yeah?
Does it also terminate at a set point the same way k-means would, or do we need to tell it when to stop?
So it's a great question. This algorithm will also terminate, for example, when you can always do, mu1 at iteration k and compare that with mu1 at iteration k plus 1. And so you can look at how much the parameters of your Gaussian distributions are changing. And when that gets below some tolerance, you can say, there's no point continuing because I found a local minima to this objective function. So that's how in practice this is actually learned. Yeah?
Just on slide 33 where you mentioned the log likelihood equations.
Yep.
Why is it that you said that there we're assuming something about the z's and that allows us to why do we take the log likelihood of the joint probability but before we took it only of
X.
Yeah.
Great question. So the key step that makes this entire thing work is doing this alternating procedure. So in the E step, when you infer P of zi equals k for each xi, what you're really doing is originally you just had your X matrix, right? what you're now going to have is this Z matrix. So this Z matrix is going to tell you, let's say that k is equal to 2. It's going to be an n by k matrix where each entry of this matrix is going to be the probability that Zi equals, in this case, 1 given x1.
And this is like we're assuming that we're given this matrix.
No, you're going to compute it. So that's the key point. So you don't have the actual values of the Z's, because if you did, your problem would be solved. So what you're going to do is you're going to guess. You're going to take the current set of parameters in your model, and you're going to run Bayes' rule to infer what your latent variables are. So this X is an n by d matrix, and the Z is going to be some n by k matrix, and you're going to infer that n by k matrix. It's going to be the result of doing some computation, namely this one.
Okay, and before you were saying we just didn't do what you just said that we don't have access to it?
That's right. We still don't have access to it. But that's what the algorithm is. It's basically guess at the thing you don't have access to, pretend that that's the right thing to do, update the parameters, and then re-guess it again.
Okay, so like yeah, the first form of just x is like not usable. We can't actually do it.
The x's are always going to stay the same.
Yeah, no, just the first thing that you wrote down, just like the log p of just x.
Right. So we can't use just that to update the model parameters alone, because we don't know how to take gradients with respect to it, and because we don't actually know, and it's not like there's a closed form solution for that either. Yeah. But does that answer your question? And do you sort of see how you do this iterative procedure by first guessing the z's, and then noticing that when you guess the z, like if you had both x and z, that's what enables you to write down this joint distribution.
Yeah, so we're just making assumptions because we can't solve this problem.
Correct. You're going to make an assumption that the inferred or the guessed values of the Z matrix are the right ones, and you're going to use those values to learn the parameters, but you know that those parameters aren't perfect either, because they're made using these guesses.
Yeah.
So then, now you have new sets of parameters. So you're going to re-guess again what the Z's are.
Yeah, so it's the same thing as last time where we're like doing optimization of one variable.
That's right. Okay. And so, where does that leave us? So now, this is what EM will look like if you were to run this on this two-dimensional data set, where you could start with these two random choices for what the initial parameters of the mixtures of Gaussians are. In the first step, you would assign, these points to the red component and these blue points to the blue component. And the fact that there's some shading here indicates this degree of uncertainty. So at some point along this line, you might have a 50% chance of it coming from either one. So that's what's indicated by the shaded portion. And then afterwards, you would update the coefficients associated with the mixture of Gaussians. So you would update both the coefficients as well as the mean and the covariances, which would give you these ellipses. And then again, you would throw out the old values of Z and re-infer what the posterior probability of Z given X was, which would give you now these red and blue points. And then you would update the parameters of the Gaussian mixture components again. And over time, at the 28th step or so, you would allocate all of these to the red component, all of these to the blue component, and call it a day. And so, how does this compare to k-means? And in many, many ways, the two of them are very similar. In k-means, you had the assignment step, which is to assign each point to the closest cluster, and the refitting step, which is to move the cluster center to the average of data points that were fit to it. Versus in the EM algorithm, you would compute the posterior probability of Z given our current model, and in the M step, maximize the probability it would generate the data it is currently responsible for. And so there's lots of similarities between the soft k-means algorithm and the EM algorithm for Gaussian mixture models using a shared covariance matrix, which is 1 over beta. So what you can actually show is that this process of EM is identical to doing soft k-means if you set the covariance matrices for your Gaussians, each of the p of x given z's, to be 1 over beta times the identity matrix. And so both of them rely on alternating optimization methods and can suffer from bad local optima. So it's something to be worried about. Yeah?
Is beta, is that just like a random constant?
No, so remember in soft k-means we have this parameter, this hyperparameter beta, that, yeah, it's the same beta. So it's basically saying that if you wanted to relate the two to each other, you would basically find the beta that you use for soft k-means. You would set the covariance matrices to be 1 over beta times the identity matrix, and then you would be able to see that the E step and the M step in EM for the corresponding mixture of Gaussians would be identical to doing soft k-means. Like you'd get the same solutions out. And this goes back to another question your colleague asked, which is what happens when data is not circular. Like that's why we use Gaussian mixture models, because you can use the covariance matrix to model ellipsoid shapes and more complex shapes in higher dimensions. Okay, so there are another set of slides on why EM actually works, but I'll give you all the choice on whether to go into it. So there's two options. I can either spend the last 5 or 6 minutes talking to you about whatever you want. Happy to talk to you about jobs, machine learning in general, in industry and academia, research, what we do. Actually, just any questions that you have, or we can go through the optional ones. So I'll let you all pick. Who votes for question? Q&A. Okay, that's about what the other class had. So, all right. So these are optional slides, but I do encourage you to check it out if you're interested in the material. And if you have any questions, come by office hours. But for now, for the next 5 minutes, questions that people have. Yeah.
So I wonder if that framework can work in related to learning, you have to graduate.
So I don't think you have to pursue a graduate degree to work in industry in machine learning, but how graduate degrees sort of help you skip a few steps is the only thing that it does. So think about it this way. Like in machine learning, particularly right now, it's sort of a really cool and exciting time because there's a lot of open source tools and things out there that are available for you to make stuff with. So if you're interested in long-term an industry career and you want to go out there and build, for example, an indie game using variations of GPT as well as some of these new AI-generated video software, you can do that right now with the set of skills that you have. You don't need to necessarily go to grad school to learn how to do that. Because ultimately, if you want to release something to the public, there's nothing that grad school will teach you that you couldn't already learn on your own. In general, that's true for most grad school, and I say this as a scientist. But you should think of going to grad school if you're really, really interested in understanding why things work. Because if you're interested in understanding why things work, then grad school gives you a couple of years where you have the freedom to explore that question. And exploring that question often yields answers to build the next version. So if you're really interested in knowing, like, what is the next iteration of GPT going to look like, and how do I build something that isn't 500 billion parameters, but rather like 1 million parameters and has the same like productivity and output as GPT does right now, that's a question that is really interesting to study in academia. Because there's no industrial use case for that question yet. No one will pay you money to, at least not yet, to like make GPT so small, because it might be years before you have an answer to that question. So that's kind of how you should think about the trade-off between them.
And I've noticed that most machine learning related jobs, they ask for experience. And when you work in that industry,
What do you show as experience?
and also like what should we start working with?
Yeah, so a couple of pieces of advice. First, and I say this to all undergrads, the best piece of advice I can give you is to make a website. If you don't have access to a toronto.edu like domain space, it's fine. Use GitHub pages. It gives you a mechanism to make a free website, and everyone should do it. And what you should do is start creating a portfolio of open source projects that you put out, or questions that you're really interested in, or things that you blog about. All of this, like having a mechanism for a space on the internet that represents you, is one of the ways by which employers will do some form of verification, even beyond just looking at your CV and transcript. So it's always worthwhile to have a academic web page. Even if you think there's not much to it, even like a simple photo, here's who I am, here's what I do in my spare time, and here's some projects that I've completed, that's sufficient. Yeah.
What kind of stuff do you do in like your research?
So I work on two topics. The first topic is much more methodological. So we work on a lot of problems relating to how we can build intelligent systems that are capable of distinguishing cause and effect. So over the last decade, we've gotten very, very good at building predictive systems. So we know how to solve systems that can build predictive functions from very complex high-dimensional data like images, text, speech. What we don't yet know how to do very well is create robust predictive systems. And that's where I think ideas from causal inference can prove very influential. So causal inference is sort of a slightly newer field. It was only formalized like, let's say maybe 40 to 30 years ago, and it's been studied in biostatistics, econometrics, computer science, and it's basically the idea of how do you truly know what the effect of some change to a system is using data alone. Because when you or I move to a new room, well, we know how to use chairs, pencils, projectors, computers in that new room. But machine learning models are surprisingly brittle to that kind of modification to their environment. And you know, it's sometimes harder to see these edge use cases in the context of GPT-4 because it's trained on so much data that it's often even difficult to know what is out of distribution for this thing. But there are lots of research studies trying to showing that there are scenarios in which these kinds of neural networks fail. But robustness is one of the big reasons that I do the methodological research work that I do. And so in that kind of work, it's a mix of statistical methods and linear algebra and conditions for identifiability and neural networks. So kind of a mix of stuff. And on the other side, I work with applications in healthcare. So I work with the hospitals. And the reason why I care about causal inference is because that's the thing every doctor wants to know. They want to know, how do I treat this patient? And the answer to that question is the result of asking, what will happen to this patient in the short and long term if I choose a different intervention from the one that I actually end up giving to them? So that's the question they want to know, and the answer to that question requires developing new methods for causal inference. More questions? Yeah.
For the project, to what extent are we allowed to use tutorials for things that are not focused on the market but are kind of exciting?
I think it's okay as long as you cite it, particularly if you're doing the open-ended one. Yeah. Any other questions? Yeah.